The third graph for exponential graphing, third video for exponential graphing, applying transformation. So bringing it all together here so we can sketch graphs. And exponential graphs, remember from our previous work, we're using that essential form and parameters to help us determine the transformations. Okay, so we're building on the last two videos. These are the main points, and then we're going to employ these main ideas. So the capital A, not to be confused with the base, the capital A, that constant dilates the graph vertically. Now you've seen that before with various other types of functions, notably parabolas, quadratics, and a similar idea in terms of amplitude with trigonometric functions, and likewise with other functions. So when A is greater than 1, it's stretched vertically by a factor of A. And when it's between 0 and 1, it's compressed. Now if it's less than 0, of course, we have that from 2 videos ago, we have that mirror image about the x-axis. So that basically is a shape change. B dilates the graph horizontally, and it dilates it by a factor of 1 on B. Bit like what you might have seen with the period in the trigonometric graphs, the horizontal compression. So the bigger B is, the more compressed it is, and if B is between 0 and 1, a decimal, it's stretched horizontally. So it's stretched by basically dilated by a factor of 1 on B in the horizontal direction, from the y-axis in other words, whereas A was from the x-axis. So A and B are shape changes. So when we're talking in a minute about the shape, we're talking about A and B. Parameter C is a translation, and it translates the graph left when we have positive values for C. So you can see C is up there, like B, C is up there in the exponent, in the index, and basically you get horizontal translation to the left if it's positive, and to the right if it's negative. This is a little bit like the model we have used in the past with trig functions. You might be familiar with that. Lastly, the final one, D. D is also a translation, as we mentioned earlier on. D, if it's positive, it's D units up, or negative, D units down. So A and B are shape, C and D are position. And with those four, we have enough to do a very reasonable sketch of an exponential. First example is 3 outside of 2x plus 1. So the first thing we do is to compare the equation with the general exponential function, which we just saw. A in this case is 3, capital A, and B, well, let's have a close look at that. If we just get the power aspect of it, so B would have been outside the brackets there. Now all we've got is just 2 to the x, so it's pretty obvious that B equals 1 here. Now C, if we write in the full form of the generic form there, the general form, we can see that C is 0. There's nothing there on paper, so nothing there in print, so C is 0 and D is clearly 1. So that's important. First thing we do is establish the parameters and compare it with the generic or the general exponential function. Now what we look at is the basic shape, and then we put in a significant point to help us out. So if we look at the basic shape, we're considering A and B. Now A and B are, if we look at them up there, they're both positive. So we'll note that. So this is good setting out, a good justification. You don't just sketch it and say, da-da, that's it, because you can just take it off your graphics calculator. We want to see you understand what these steps mean and what these ideas entail. So it's important. This is essential justification for this course. So you need to show all this. So they're both positive. So the shape, shape will be similar to a familiar one. So let's use a very familiar one, y equals e to the x. So it'll be that basic y equals e to the x shape. E to the x is a known, it's a definite known. So we tend to use that. Okay, so it's a it's a touchstone, if you know what that phrase means. So we'll use that as our reference in this case. So they're both positive. We have that upwards J shape. For the significant point from our previous work, we know that let x equal 1, and so we'll have y equals 3 outside of 2 to the 1 plus 1, and that's 3 by 2, 6 and 1, 7. So we have the point 1, 7 when we plot it, and we'll note that that'll give us an idea of how quickly it's rising compared to other positive other exponentials with positive a's and b's. The horizontal asymptote, which we looked at previously, that's a case of when y equals d. Just remember a generic one exponential would have the asymptote at like something generic like y equals e to the x has the asymptote at y equals 0. So we know that it's y equals d based on our previous work. So if we look at the equation, it's plus 1 on the end for d, so d is 1, so y equals 1 is the horizontal asymptote. Last step there we can see is the x-intercept, and the x-intercept is when, sorry, the y-intercept is when x equals 0, pardon me, y-intercept is when x equals 0, so we sub that in, y equals 3, 2 to the 0 plus 1, which is 3 times 1 is 3 plus 1 is 4, so we have 0, 4 is where it cuts through the y-intercept. If we put all those things together, there's our we can see that's our finished result. Of course, use your graphics calculator too, so you know what you're chasing. Like all the curve sketching before, perhaps even put it in the graphics calculator first, right? That might be smart, but certainly make sure you've got it there to verify. Okay, so graphics calculator to verify, and you might even want to write that verified with GCalc. Definitely use that as a guide because it's there, but of course you need all of this justification as well. So it's if we base it on that touchstone y equals e to the x, it also does all the things that this does. Essentially it has that shape. The differences are, so it's got that positive shape, but with the shape we put in that point that we were talking about, the significant point, which if we just go back up here, we've written that to the top left of your screen. When we let x equals 1, we put that on. The other point we know about is 0, 4, the x-intercept. We can put in our y equals 1 asymptote and put in a nice faint dotted line there and label it, and basically we've got 2 points, we've got a shape and we've got an asymptote, and we've got enough there to sketch. Let's look at a different example. We've got an exponential here which we need to sketch, y equals 1/2 times 10 to the x minus 1, and basically we need to compare it with the general exponential. So there's the general exponential, and we write down a is 1/2, b is 1, okay, because you can tell by the coefficient of x it's 1, c is -1 in this case, d is 0. So looking at the basic shape and using a significant point to assist us here, again A and B are positive, so the shape is like our typical y equals e to the x, so it's got that regular positive rising shape. And the significant point when x equals 1, y equals 0.5, so that will guide us in terms of the shape. Horizontal asymptote, couple ways of thinking this through. Either you could look at d equals 0, so y equals 0 will be the asymptote, or in other words, as we saw in the previous video, if we take extreme negative, or as x approaches negative infinity, y will approach 0, so the asymptote is basically the x-axis, or the line y equals 0, and the y-intercept is when x equals 0, and we get that point there. And we can see we've got two guide points, and we've got that positive shape with, you can't see it in this diagram, but it would be a good idea to note the asymptote is going along the x-axis there. So different, but not really any more difficult. Okay, we have a more difficult one, and again we go through those same steps. We compare with the general exponential function. A is 2, we've got B -3, C is 1, and -5 for D. So we've got to consider the shape, and this time B is negative. Now we've got to remember our lessons from y equals e to the negative x. Those are mirrored in the y-axis, because we saw previously that if we look at, if you bear with me for a second here, if we look at some of these ones that have, if we compare these two together, and essentially this red function and this blue one are y equals 2 to the x and y equals 2 to the negative x, because if you've got, see, I could replace this one here, 2 to the negative x. Okay, so if I replace that with what we had, y equals 1 over 2, and it's the same function, isn't it? Look, so 2 to the negative x and a half to the x, essentially you're changing the base, aren't you, due to your index laws. Okay, 2 to the negative x is a half to the x, see? Okay, because 2 to the negative 1 is a half. So that's why it's mirrored, and we saw that previously. So that's something to bear in mind. So all of our skills are culminating. So let's go back to our screen, and we've got our shape, and we need to look at a significant point as well. Significant point when we set now x, this is a little bit different here. If you tried to make x equal to 1, see, it's different because of the negative here, and it's got the opposite shape. So we tend to make x equal to -1 for that significant point. Do you see why? If you have a look at the, you can get your graphics calculator and plot it, and you can see because of the reverse shape, if we used x equals 1, we'd have something here. That doesn't help us. Remember, we want to see how it rises, but we're rising in the opposite direction, or we're reading the function backwards in sense of the x values, and we need to go back 1. Okay, so just always consider that significant point's got to be, remember what we were saying in the previous video, it's got to be useful in determining how it's rising up initially. And so if we go x equals -1, it's also easier to sub in, alright, because when we go -1 plus 1, that'll be e to the -3 times 0, which is e to the 0, and it also does help us determine the rise there. Okay, so remember b is -3, so the 3 means, remember, the shape has changed. Okay, so it'll stretch it out horizontally, and that affects the rate at which it climbs up. And you can play around with graphing software to show you that there. So if we have this red graph again, and if I put in B there and add that in as an extra parameter, this compressing horizontally looks a bit like this when you, so the compressing horizontally actually makes it look like it goes up steeper more quickly. It's actually, we're compressing the horizontal, which actually makes it appear that it's getting vertically pulled up, but that's not true. It's just the fact that everything's happening quicker along the x-axis. So next we've got our horizontal asymptote. So remember, this is going the other way, so instead of x approaching negative infinity, we've got to approach positive infinity, or just look at the value of d and it's -5. Either way, y equals -5 is our horizontal asymptote. The y-intercept is still in x equals 0, and we get -0.49 is where it crosses. Then we have enough information to sketch it. Lastly, we're looking at, I guess, using some good language to come up with a really good answer if you're asked to sketch a graph. If you're asked to use transformations, I'm not asking you to reject everything else from earlier in this video, but maybe also include these ideas that we can see here. If we have to transform e to the negative x plus 3 plus 1, we're essentially doing the same as the rest of the video, but including some justifications for going from the base e to the x to what you see there. So it's about the language you use and the justification. So you can use all those previous steps plus include these as part of your justification. So basically a equals 1, so the shape, the vertical stretch isn't really apparent at all. It'll look like e to the negative x. So you can start by drawing e to the x if you want to do it in stages, and I guess this is just an alternative method, and then draw in e to the negative x because we've got b equals -1. So step 2 could be doing that. So on the graph you can see that they've started with e to the x first, and then green, they've reflected it there. So that's an easy step to do. And then and these verbal or textual explanations are very important. The next thing is the C. Alright, so C is 3. So once you've reflected it, then you move to C. So get the shape right first. Alright, shape first and then translations. So that means it's translated 3 units to the left. Now be careful because it said positive values of C, okay, to the left, and that's what our earlier notes said, okay, positive values of C to the left there, and that's regardless that C 3 units to the left, that positive 3, regardless of whether we have a negative or not out the front. Okay, so using those brackets is really helpful. You can see the purple graph is just drawn in there. It's a translation to the left. So going from the green to the purple, you can see they've got the graph there. Coming down there, D, moving it all up by 1, and you can see that that's the finished graph. So it's this graph here, and they've also marked in the asymptote. That last step is the translation up. So that's an alternative way, and it might be more suitable for some graphs. Certainly